Welcome to the second session. So in the second session, our next speaker is Professor Rajesh Ranjan. And before we start the next session, let me briefly introduce our next speaker. Dr. Rajesh Ranjan is an assistant professor in the Department of Aerospace Engineering at Kanpur. His research interest includes turbomachinery flow, unsteady aerodynamics, flow instability, and mathematical modeling. He did his postdoc from Ohio State University, USA, on project sponsored by the Air Force Research Laboratory. His PhD is from the JNCSR Bangalore, where he worked under the unsteady simulation of turbo machinery flow under guidance of Professor Radam Narasimha. Prior to that, he did his master in aerospace engineering from ISC Bangalore and a bachelor in chemical engineering from BIT Sindri. He has 3 years of industrial experience with Tata Computational Research Lab, Pune. Apart from his primary interest in the aeronautical field, he has also extensively worked on the COVID-19 modeling, especially on the first and the second wave in India. Dear all participants, with this brief introduction, I would like to welcome Dr. Rajesh Ranjan to address our participants. Dr. Ranjan?
Yeah, sure. Let me share my slides.
Yes.
So, should we share the screen or the window? Window maybe, right?
Yes.
Yeah.
Yes,
can you see my slide?
Yes, sir. We can see.
Okay. Yeah. So, welcome everybody in this afternoon session. And we had a very inspiring session this morning by Professor Suman Chakrabarty, and he talked about how fluid dynamics is related to the medical or the biological thing that we talk about. And it was a really inspiring session, and he discussed about like how it is necessary to innovate or necessary to think about new ideas, which is different from the traditional fluid dynamics. So, for example, many people do like flow past a cylinder, which is a good fundamental research, but then we have to go and make this fluid dynamics accessible to different kind of applications. And with that respect, the today's talk is about unsteady dynamics of flow behind a military transport aircraft. So this is little change in gear. So this is going to be highly turbulent flow, as you can see here. That's a U.S. Air Force aircraft, and the flow getting developed in the back of that. Okay, so before I start my presentation, it can be different than what it was in the morning. So in the sense that if you have any question, please interrupt and ask. So what I will do that my talk is divided into several parts, okay, several segments. So basically, after each segment, I will take a pause and I will ask if you have any doubts, any questions, and any clarification. And if you don't, I'll move ahead and go to a different segment. So all the segments are correlated. It's about the same flow physics and how we are going to use different kind of tools and techniques to analyze different aspects of this flow. Okay, so all segments are related, interrelated, but then they discuss about different aspects of the flow. So let me start. So I once again welcome you all for my talk. So this is work done with Professor Datta Gaitonde at the Ohio State University. And before I start my presentation, let me acknowledge all the sponsors. So first, this work was done when I was at Ohio State University, and I'm still continuing that in the lab called HFC MPL, High Fidelity Computational Multiphysics Lab. And then this project was sponsored by Air Force Office of Scientific Research. And there are different centers like OSC, Ohio Supercomputer Center, is something like CDAC here, which gives the supercomputing power. Similarly, we had the Department of Defense HPC modernization program, which gave us the support for the HPC. Okay, so let's move forward. Now, what is the motivation behind this talk? So those who belong to the stream of aerodynamics, or those who are generally interested in the field of aeronautics, would not this news about 1 month ago. So Indian government had signed a deal with Airbus and TASL, which is Tata Advanced Systems Limited, of around 22,000 crore, where they will get C-295 aircraft, which is basically a military cargo aircraft, around 56 of those numbers. Okay. So this negotiation was going on since 2011, and now it got finalized. What is important is that of this 56 aircraft, the 16 will be directly delivered by the Airbus, who has designed this aircraft, and 40 will be made in India. And the technology transfer will be done to TASL and the different Indian government bodies, and they will together manufacture this 40 aircraft in the next 10 years or so. Okay, so why this flow is important? So if you look at this peculiar C-295 aircraft, so if you have seen the aircraft, for example, in the airport or anywhere, you would not notice this kind of upsweep angle. So if you can see my highlighter here, this is unusually high. So if you measure it from the baseline, this angle is unusually high. This kind of angle,
Hello.
you will not. Yes.
Sorry for interrupting you, sir. Your PPT is not visible.
My PPT is not visible?
Yes, sir.
Is anyone else can see my PPT?
It's visible.
It's visible, right?
Yes, sir, visible.
Yes, sir, visible.
Okay.
Yes, sir. Visible, sir, visible.
Yeah. Okay, so I mean, whosoever said that it's not visible, please make sure there may be issue at your end. Okay, because here I see that I'm sharing the screen. Okay. So this is called the upsweep angle. This angle that you see that, so this is the forebody of an aircraft, which is typically of a nose shape. And then the mid portion, you will have the aircraft wing. And then depending on what kind of engine you're using, so whether it's a turboprop, a turbojet, or a turbofan, so you will have the engine system mounted on the wing. And then there will be after body configuration. So this after body configuration is what I'm interested in, because it leads to very beautiful fluid flow phenomena, as you will see in the next few slides. So one thing to note here is that this upsweep is very, very high in the military cargo aircraft or in general cargo aircraft. And what is the reason behind that? Is that because the paratroopers need to jump, right? So they have to jump from here. So there's a cargo door located here that needs to open whenever it is needed. So when you need to open a door, so this door will open like this, right? The door will open. So if it is very close, suppose upsweep is very less, it will basically go down against the gravity and things might fall. So what they do is that they make it more upswept so that there is no difficulty in opening the cargo door. So that is a requirement from the military side or from the cargo side, and that leads to a very beautiful flow phenomena. So these are some of the other military cargo aircraft. So we have C-130J, and there is a modification to that, C-130J-30. Then there's A-400, C-17. So all of them you see is a very large upsweep. Okay, so the upsweep angle is quite high in all of these aircraft. And this configuration is called upswept after body configuration. Now that we know that this upsweep angle is high, what are the kind of fluid dynamical phenomena that we expect? So one thing, if you're working in fluid dynamics, you would note that the flow has to turn around here. The flow is coming at the bottom like this, and it has to turn around here. So when there's a big turning involved, you should expect a separation. Okay, and because of the separation, you will have shear layer, and those shear layers can basically lead to different kind of vertical structures, and that is what is happening here. So these aircraft have high aft fuselage upshape to incorporate doors, which is denoted by the angle P here. I would request, please, all of you to mute your mic unless you have a question, because it is interrupting here. Okay, so just to show you a comparison, so the transport aircraft, typically, for example, if you see this Boeing 777, so they have upsweep around 14 degree. So typically you'll have upsweep like 5 to 15 degree. The regional aircraft, which are the small aircrafts, okay, so they can go a little high, 19 degree. The cargo aircraft, for example, if you look at C-130 that we saw in the last picture, or even here, it's also called the Hercules. It has upsweep around 28 degree, which is very, very high. Okay. So this high upsweep causes separation. So this kind of separation will get developed if you have a high upsweep, because the flow has to turn around. And depending on how much upsweep you have, you might have different kind of separation. And this separation will lead to the separating shear layer, and they would roll up. So I will talk in detail about those phenomena, but this roll up will create streamwise vortices. Okay, so these vortices basically meander in time. So you can see it's a very complex configuration. So you have a shear layer and you have a vortex, and the vortex is in the unsteady way. It's not like a very nice vortex. It has kind of meandering, which means that the vortex core is moving here and there with time at every distance. So that is detrimental to performance. And why it is that? So if you look at the picture on the right, so although this is showing the wing tip vortices, but that is same thing is true for the after body vortices also. So if you have a vortex set out by a given aircraft, and there is another aircraft approaching, it might get trapped into this after body vortices, the trailing vortices, and that may be detrimental to this approaching aircraft. So because of this reason, what happens that suppose you have a lot of this kind of aircraft, then in the airport, you have to make sure that one aircraft has taken off sufficiently ahead in time, so that other aircraft do not get trapped into their trailing vortices. So these are the kind of problems that you have when you have these kind of after body vortices, or for that matter, even the wing tip vortices. So this is again from our simulation that I will discuss today. So it's a very, very complex structure. So we talked about the performance, but fluid dynamically also it's very, very complex. You can see there's a large structure, the blue and green, that is blue and orange. This is orange one and this is blue one. So these are basically the main vortex, but around that you have very small structure, right? So all kind of scales possible. And if you look at very close to the after body, so this is basically the upsweep region, right? So here it looks like a rib kind of structure, right? So the structures are forming and they're getting entangled into these large vortices, and these vortices move in the downstream, right? So there are other competitions also which shows different kind of beautiful structure that you see downstream of the flow. So what will be the basically the overview of my talk? So I'll talk about the computational approach. So I am a computationalist. So I will mostly talk about the computations and the analysis. And whenever the analysis comes, I will try to go a little bit pedagogical and try to explain what this analysis means, so that even if you're not working in this particular problem, you can use these ideas or these tools for your own problem. So for example, all the tools that I'll be using today will be useful for any unsteady flow. So because this is an unsteady flow where you have a given mean and there's an unsteadiness on top of that. So there will be unsteady flow, and all the tools that is being used here will be useful everywhere. So then I'll talk about the characterization of the flow. So how to characterize this kind of flow, different kind of fluid dynamical aspects. So for example, what happens if you increase the upsweep angle? So because different aircraft have different upsweep angle. So you would expect the separation will be different, the vortex structure will be different. So I'll talk about that. How the vortex meanders behind the aircraft. That's another topic. Another topic, many of you might be working on the compressible fluids, right? So if you look at these aircraft, they work in a scenario of around Mach number of 0.5. So it is compressible, right? So when it is compressible, there are certain changes that happen, and that basically affects the performance of the aircraft. So I'll talk about the compressibility effects. And if time permits, I will talk about two more important aspects. One is basically the hysteresis. So this kind of flow also goes through hysteresis. Basically, based on different initial conditions, you will have two different flows. So typically, you would have learned that the solutions would be unique. Like if you solve a Navier-Stokes simulation, the solutions would be unique. That is not what happens here, both in the experiment and the computation. And there's a good reason behind that. So if time permits, I'll talk about this hysteresis. Well, you'll have two different results or two different flows at a given set of parameters by just changing the initial condition. And then a little bit about the flow control potential. So let's move ahead. So what are the computational approach? So this is the typical simulated military cargo aircraft after body. So they discussed that you will have a ellipsoidal nose, which is the forebody. Then there's a cylindrical body where the wings will be mounted and the engines will be mounted, right? And then there will be a after body, which will have the upsweep, right? So our interest is the upsweep here, right? So what we'll do, we'll not simulate the entire body. So basically what we can do is that if I know the flow here somewhere, for example, here, I can just get the flow here, and then I let the flow develop in the after body of the aircraft. So this is what I do, that I take the boundary layer from the experiment. So the experiment will have these results or from the flight data, and I put it on there. And then basically I run the simulations using large eddy simulation. So large eddy simulation is a kind of approach, those who are not very familiar with, where you basically simulate basically the large eddies and the model the small eddies. So we have like three kind of approaches typically. One is the RANS, where you model everything, okay, including the large eddies and the small eddies. And you have at the other end, we have DNS, the direct numerical simulation, where you basically do not model anything. You basically simulate the large eddy as well as small eddy. But as you'd expect that if you want to resolve every single flow at very small scale to very high scale, you need enormous resolution, and then it becomes very, very expensive computationally. Right. So large eddy simulation is something in between, where it will resolve the large eddies, which are of our flow of interest, and the very small eddy can be basically modeled through different kind of models. So there is Smagorinsky model. What we'll be using is called the implicit large eddy simulation, where there is no explicit model, but the filter that we are using basically takes care of the modeling of the very small structure. Okay, and these things I want you to remember, because I'll be coming back there again and again. So X is the streamwise direction. The flow will be in the streamwise direction X. Y is the wall normal, so from top to bottom. Okay, and Z is basically, if I can call it, although it's axisymmetric, it's kind of if you take the center of the cylinder, so from left to right. Okay, so top, bottom, left, right, and front and behind, right? So these are the three directions we have. And the length of interest, length scales, is basically, one is the diameter. So this is the diameter of the cylinder. And depending on the upsweep, so you would notice that if the phi is high, right, so the L will be small, right? So L is what? L is cos phi, right? So if the upsweep angle is higher, this L, which is the how much is the base is elongated in the direction of X, right? So that length will be smaller depending on the if the phi is high. So these are the two length scales which are of interest. And we perform computations. Okay, so again, for the terminologies, because they will be important later. So I call this point as an upstream apex. So this is the point where the flow first meets. So the flow is coming around the cylinder and then it has to turn, right? So this is the point where the flow has to turn first. So that point is called upstream apex. And this is the point where the flow leaves. Okay, so the maximum downstream point is the downstream apex. Okay, and this is the base. This is the upstream base. And the flow is in this direction, right? There were similar efforts on the computations on the experiment side at the Florida State University. And you can see that this is the model they used. This is mounted here. And we basically got the modular parameters from here and put it in the flow here and just simulated the after body. Okay, so this is how the grid looks like. So if you look at the zoomed region, so this is a curvilinear grid and it's a structured grid. So making a grid was quite a tedious task, but once you make the grid, you can use your curvilinear coordinates and high order schemes, which will give you a much accurate results. So that's why we went through that approach. Okay, so this is the upsweep region, and you can see that grid is very fine close to the upsweep region, and it becomes coarse as you go up away from the body. And basically we had the far field boundary at the 12 diameter, and this will be a complete cylinder. The 14 diameter will have a complete big cylinder, which half of which is shown in the green region. So this is just only the half region shown. The half will be at the bottom. So if you look at the grid in full, it will be a complete cylinder, right? In which you have a upswept after body cap. So again, this is the same view. And if you look at here, this is where we put our modular parameters obtained from the Florida State University. So we use a 4th and 6th order compact scheme. So compact schemes are basically, it's very nice if you can make a structured grid. Okay, so it can be used in a curvilinear coordinate system or even a general coordinate system, but you need a structured grid. So this is a kind of finite difference scheme, but it's compact because you can stretch the stencil in either direction and you can make it higher order. So whenever you use this compact scheme, the flux scheme, you need a filter, because if you use the compact scheme, you will see that there are some unwanted energy which is coming out, and you need to filter them through a low pass filter. So there's a compact filter which is being used along with that. So typically, if you have 4th order compact scheme, usually just 6th order filter. So 2 order higher than the. And then we use the beam and warming implicit time stepping scheme. Okay. And as I told that we have taken the modular data concurrent with the experiment from the State University. And the time step used by was around 2.5 to 10 per 4. Now, any computation that you perform, you will have this question that have you done the grid convergence study? And that's a very valid and important question. So what we did, there are 2 ways you can do the validation. So one is basically increase the grid size. So we have used a grid of around 60 million, right? So either you can make 60 to 100 million, or on the other way, what you can do that you can increase the order of the scheme. So what we did is C4 is basically 4th order and C6 is basically 6th order. So we increased the order and checked whether the solution changes. So this is kind of pH. Those who are from finite element background, you would know that this pH kind of distribution, right? The P, the polynomial order, and H is basically the grid size. So either you can increase the P and keep the H constant, or you increase the H and keep the P constant. So both would have the equivalent effect. So that's what we did, that we just kept the grid same, because the making the grid is a very tedious task. And we just increased the order of the scheme, and we found that the solution remains the same. And this is pressure coefficient. I'll discuss more about it. on the symmetry plane, basically at the center of the base. And these are three different angles: 20 degree, 32 degree, and 45 degree. And basically there are three different regions, and you would notice that these flat regions that you see is basically the separation bubble. The other important thing is basically our simulations are done at Reynolds number of 25,000. Okay, so you may ask that flight Reynolds number are quite high, so it may go up to 1 million. So if you are doing a simulation at 25,000, are you basically mimicking at least qualitatively the flow features? Right. So our answer to that is yes, and it has been seen experimental studies also, and here also we show. So for example, we go from 25,000 to 50,000, the two different Reynolds numbers, and what you see basically these are the vortex positions. Okay, the vortex that you just saw. You would expect that they will develop in the base and they will be symmetric, the two vortex, right? The top vortex and bottom vortex, and how they are changing in position. Okay, so you can see that when we changed Reynolds number, there was not much effect in the change in the position of the vortex. So it has been found, and we also saw in our simulations that if you basically perform above a certain Reynolds number, the qualitatively the result should not change. So for example, if you are looking at the vortex, you will still have the vortex even if you go to the million Reynolds number. The strength may vary because that will depend on the Reynolds number, but the qualitative features will remain the same. And again, we are limited by doing 25,000 because of the grid requirement. Even in LES, it is not easy to go to a very realistic Reynolds number because your grid resolution will become very, very high. So how does the flow field look like? So let's go there. Before that, so most of the results that I'll be discussing about three upsweep angles. Okay, so 20 degree, 32 degree, and 45 degree. So why up to 45 is because typically the upsweep angles in the aircraft, the cargo aircraft, is about 30 degree, 35 degree, something like that. So it is always going to be below 45 degree. And above 45, something else happens. So these nice vortices that you see, they will no longer be there, and there will be a wake region. So because there will be huge separation, and these vortices that you are seeing forming on the base will not be there. So that's why we limit our study to up to 45 degree. So this is the LES flow field. This is actually obtained from an LES simulation. This is not a artistic impression. So this we got simulated the flow field at 32 degree of upsweep, and then we use the Q criterion. Okay, so the Q criterion basically extract the vertical structures very nicely. So at certain Q criterion, maybe I think Q equal to 10 here, and then we colored with the sign of the streamwise vortex. Right, so that's why you have two different signs, the blue and the orange basically signs here. So that shows that the vortices are counter-rotating. They're not co-rotating. They're rotating in a different direction. So what happens, like when the flow comes here, so this is the first point that they are going to meet, right? This is the nearest point on the cylinder, and it has to turn a lot here. So when it tries to turn here, you will have a separation bubble, as you can see in point 1, right? So this is the separation bubble that gets developed. In all the cases, I'm showing it for 32 degree, but this is happening with 20 degree and also for 45 degree, right? So the flow has to turn, the separation bubble will be developed. The size may become different, the character may become different, but there will be a small separation. Okay, and this separation, what happens? So although it separates here and here and here, so what happens? There will be separated shear layer. So after the separation, the boundary layer basically evolves to the shear layer, and this shear layer will roll up, and you will have this kind of teardrop structure. So basically, if you have a body like this, so they will be wrapping around the body. Okay, at this location 2 here, right? So you have a nice teardrop kind of structure, so which are basically attached to the body, right? So from both the sides. And what will happen that these shear lat that you see that are attached to the body, they will feed on the basically flow on the body, right? So they will keep on taking the energy from the main flow, and they will start growing, right? So if you go to the position 3 here, so these tiered up structures which are like attached to the body, you see that now they have become very big and become more like a circle, right? It becomes very circular. And then the attachment to the body is also reducing here, right? And if you go further, for example, if you go to point number 4, they are completely detached from the body and they're completely circular. So you have a nice counter rotating vortices there. And this region that you see here on top is basically the shear layer that is coming from here. So there's a flow which will be coming from the top, right? So that shear layer is here, okay? And if you go sufficiently far, so for example at 0.5 here, so it is away from the top shear layer. So you see that the shear layer diminishes, it's not there because it is very close to the body, but the vortex exists. The vortex exists for a quite long distance till the viscous dissipation really makes it die away. Okay, if you look at the instantaneous structure for that, right, it's really very, very complicated. So this is the same flow as the left one. The left one is the mean flow, and right one is the instantaneous flow. So if you take, for example, thousands of these structures and average it out, you will get a mean flow like the one on the left. Okay, so the left one is the mean flow and right one is the instantaneous flow. And if you look at the video of this instantaneous flow, so this is how the instantaneous flow will look like. These two vortices will look like. So this is the aircraft after body, and then we will have interaction between vortex and the shear layer. So these vortices will interact with the shear layer which is coming from the top. There will be interactions between the vortices. Right? There are two vortices side by side. They are counter rotating, and they will basically interact with each other. And you will have different kind of instabilities. I'll go into details into those things. Okay, whether it is the instability on the vortex, the convective instability, or you have instability at the base. So the base also there is a flow, and there could be a global mode there. Now, simulation parameters, as I said, that we have 20 degree, 32 degree, and 45 degree, three kind of angles. And if you look at the flows on these three angles, right? So these results are for low Mach number, Mach equal to 0.1. So you may note that at 32 degree, the vortices are a little thicker compared to 20 degree, but thinner compared to 45 degree. So that's one quick observation between these three. And similarly, if you look at these streamlines which are wrapping around the vortex, so starting from the downstream apex to the vortex where it wraps around, so this you can think of as a separation region. So there is nothing here. Okay, so this is a separation region. So this separation region increases. So here you actually, it's so small that you can't even see here at 20 degree. So as the upsweep angle increases, the separation increases. See, it's increasing here. The top one is just to ensure you that what you are getting is right, because both the experiment and LES, the left one is the experimental data through 3D PIB, right one is the LES data, and they both show you similar kind of structures on the vortices. Okay, so up to this point, if you have any question, please ask, and then I'll go ahead and characterizing the flow. If you have any doubt or if you have something that you're missing out, not understanding, please let me know.
Yeah, Dr. Rajesh, I think it is a really good talk. My doubt is like, what are the kind of computational resources required for this kind of work? How many processor cores and, this kind of information can you please give?
Yeah. So that's a good question. So we have done the simulations typically using around 2000 cores, 2048 cores. Okay, so it's around, so resources required is quite high. So first of all, these compact schemes that you are using is expensive. So although the grid points are not very large, it's around 60 million. So, but the compact schemes are expensive, and secondly, these are unsteady simulations. So you have to really run for around 500,000 iterations just to wash out the initial effects before you start seeing the actual structures. Right. So with the time step around 2.5 Newton per -4, so it really takes around, with 2000 processor, it takes around 10 to 15 days for one simulation.
Thank you, sir.
Yeah. So another thing is, what you can do is basically suppose you have done for 20 degree, done the simulations and got the results. So because these are structured grid, you can map this solution to the 32 degree and use that as an initial condition. So that will reduce your computational time a little bit, okay, actually significantly. Similarly, from 32 degree, you map the solution to 45 degree and continue with that. So if your initial condition is better, the time to settle down to the mean flow solution is faster.
So this must be your in-house code, sir, or you are using some open source code like SU2 or some other like OpenFOAM?
No, this was the in-house code of AFRL, Air Force Research Lab, that I've used. Okay. Although I also have a similar code, which is my own, that I have written by myself. But this is basically compact scheme code, and I think there are several groups in India which works on the similar schemes.
Yeah, please continue, sir. Thank you.
Okay. I'll just
Dr. Rajesh, I want to ask one question. Is this vertex or horseshoe vertex we call? Can we call it a horseshoe vertex?
Yes.
That is
these are
very
these are separate from what you see on the flat plates. Okay, so this looks like a horseshoe vertex, and you can call it, actually we name it as a large horseshoe vertex kind of structure. But the property is that you have the lift up kind of thing that happens on the flat plate. Those kind of things are not happening here. This is just one big giant vortex sitting on the base flow. There are not many several horseshoe kind of vortices. Okay. So I'll continue. If there are no more questions, I'll just take water a little bit. Yeah, so we have seen how the flow looks like, and let's go ahead and characterize them. Okay, so these three vortex that you see are for three different angles. So 20 degree, 32 degree, and 45 degree. So I've just overlapped them on top of each other. And you can see that depending on how much upsweep you have, the development of vortex is different. So when the upsweep is lower, the vortex angle is also lower. Right? It develops at a lower slant angle, if you can say that. And 45 degrees, so it has to basically honor the shape of the base, which you expect. And that is what is happening here. The second thing that you may observe is that the vortex becomes thicker as you go from 20 degree to 45 degree. Now, what about the separation bubble? Right. So the separation bubble has got a humongous effect on the drag, which is a point of interest for all the people who are interested in design. Right. So if you look at 20 degree, the separation is very close to the upstream apex, and the zoomed view is shown here. Right, 32 degrees bigger, and 45 degrees basically covering around half of the base. Right, so the same thing you can see in the CP structure on the left. So these are basically the pressure coefficient, right? So everything which is negative is basically the pressure less than the atmospheric pressure, right? So these high negative values basically denote the region of separation. So the separation region is quite high at 45 degree compared to, for example, 20 degree. And eventually they come to the atmospheric pressure level near the end of the body. Okay. So naturally, these separation will have effect on the drag also, and that we can see that if you, for example, if you take the CP on the base, right? So you have the pressure coefficient everywhere on the base, and then you multiply with the area normal and take the component in the direction of the flow. You will have the drag. So, and we are just talking about the pressure drag here, not the viscous drag, because anyway the pressure drag will be much higher than the viscous drag because of the profile that we're getting. So you can see that when you go to 45 degree, the drag increases basically from 0.1 to 0.5. So these are normalized quantities. Okay, and so this suggests that it is not a good idea to go for high upsweep, but high upsweep is sometimes a requirement by the designers because they will have to incorporate the cargo. Okay. Now, how do the vortices develop? Right. So I will take one example, for example, phi equal to 20 degree, the upsweep angle of 20 degree, and show you how the vortices get developed. Although we discussed briefly that you have a separation, and then you have a basically teardrop structure, and then you have that these teardrop structures feed on the flow, and then they become axisymmetric, and then they go out of the domain. So let's see in more detail both the instantaneous flow and the mean flow. So here you can see the instantaneous structure, so the red one, and if you look at closely, there is another one inside that. So that's called the secondary separation, the red one that you see here. Okay, so that's secondary separation, and if you actually zoom out, there will be a tertiary separation also. So this is if you have worked on the lead driven cavity, for example, so whenever the flow has to turn around, right, you have a kind of corner vortex. Yeah, so depending on the Reynolds number, you will have the increase in the number of corner vortices. So similar kind of thing is happening here, that it so happens that 25,000 you have primary vortex, secondary vortex, and the tertiary vortex. Okay, and if you go to instantaneous flow, it is much more muddled. You see the teardrop structure is not very nice, and there is interaction between the red and the blue vortex, which is much more complicated as you see here. Okay, and these tiered structures are becoming bigger. So these are the lines that where we are showing. The first one corresponding to 20% of the axial chord length, right, or the axial base length here. So that 20% we had this structure. When you went to 40%, these teardrop structures become bigger, right? They fade on the shear layer. It become even bigger when we went to the 60%, and this is the meandering that I was talking about. So in the mean sense, it looks really nice and round, but in the instantaneous sense, we'll have large, basically activity or the fluctuations in the mean quantity. Go to 80%, and it becomes even worse. And you can see that it is almost got detached from the body at 80%. And the 100%, so on the top, so we are basically cutting it and seeing it from the front. Okay, so we have a lot of CLR coming from the top here. So that will be there, and then you have two big isolated vortices in the flow. Similarly, if you go outside the field, so this is one thing that you can do computationally very easy. You know, it's very difficult to do experimentally. So even the experiments that they performed in Florida State University, so they had the probe measurement only on the body, okay, or very close to the body. So they cannot go very far outside the body, which we computationalists can do that. So we can complement that effort by showing what happens outside the body, right? So because we don't need to put probes, it is the part of our computational domain. So whatever is coming out from the body, that will evolve as per the Navier-Stokes equations. Right. So these are basically now going to the downstream in the flow, and I'm showing you at 120%, 140%, 160%, and basically 200%. Even at 200%, you can see that these two vortices are there. Although they are going, so you can see that the structure, the top CLA structure, is going up. So basically, vortex is moving slightly up, right? As you can see here. And I'm taking the section at the same distance, so that's why the vortex, the shear layer is going slightly up, although their magnitude is also decreasing, as you would expect. Now you can think of this these two vortex as the counter-rotating vortex pair. And when you think it like that, you can apply a lot of laws of the physics or laws of fluid dynamics or basically your tools to understand or characterize these vortices. Right. So one needs to find out how the what is the basically the area of the vortex or the radius of the vortex. Where does the vortex center lie? Right. So if you know where is the vortex center, you can track it and you can find out how the vortex meandered in the space. Right. So for that we use a approach called gamma 1, gamma 2 approach. So there are several ways of characterizing the vortex. Okay. So some people use the Q criterion, right? So basically you can use the Q criterion to isolate the vortex, and then you see where the Q is maximum, and then you can call that maybe that is my vortex center. Right. So the vortex will be it's like if you look at this figure here. So this is my vortex core. The red one shows the vortex core. These arrows shows the nature of the vortex. So they are counter-rotating here, and that's why the circulation is positive and negative. And the A shows the vortex radius, right? So if you go beyond A, there's very little change in the total vorticity, right? Up to this point, you'll have a lot of changes in the vorticity. There is a maximum vorticity here, and it will keep on diminishing. But beyond this area, you will have very little change. So you can call that this is my vortex core. Okay, so this is my, so you have several ways to identify the vortex core and the vortex center. As I said, one is a Q criterion. That's people who use minimum pressure criterion. So the pressure will be minimum at the center of the vortex, right? So you can use that criteria also. There are lambda 1, lambda 2 criterion also. And there are some rudimentary criterion also. What we use is basically the gamma 1 and gamma 2 criterion, which is basically based on that all the velocities will be basically perpendicular to the line connecting. So if you draw a line from here to all the way to the red line, so they will be basically normal to each other, right? So you can read more about the gamma 1 gamma 2 approach, but it's a very beautiful approach that helps you identify the vortex and characterize it. So when I use this criterion, it gives me both the vortex center as well as the vortex radius. And once we have that, we can see how these vortices develop along the base. So what am I doing? I'm basically quantifying the vortex that we got from my LES. So if you look at that, how it is developing along the y direction, along the top direction, right? So it starts very close to the base, and then it starts growing in the y direction, and it keeps on growing. Okay, and both right and so the two vortices I am showing here, left and right. Okay, so they are both overlapping as you would expect. Right. So this is basically how they develop around the base. So that G is basically the you can think of it as span y direction. So as you would expect that they would start developing symmetrically, right? Symmetrically around the symmetry line, around the center line. So that's how they start, and then they go a little bit. So you have a vortex which is starting near the separated shear layer, like a teardrop structure, and then it will start going around the following the basically your shape. And when the radius is maximum, basically at x pi equal to around 0.5, right? So when it is maximum, it will start again following the shape back to the your offset base body, and then it will start going parallelly to each other. So that's what is happening here. It starts somewhere wherever there is the teardrop structure develops. Then it starts following the profile of the body, goes a little bit outward, and then it has to come inward, and then eventually they become parallel to each other as they leave the body. These are basically vortex radius. Okay, so because there is no really vortex before 0.8, so what you have is basically the teardrop structure. There is no complete vortex, so we could not measure that. But after that, when we measured at 0.8, so whenever it is attached to the body, so it is attached to the body up to around 0.8, and after that it starts separating. It's up to 0.8, it is a higher value, and as soon as it comes out of the body, there is no flow to feed it. There is no flow to give it like more energy, right? So then it becomes a little bit smaller. Okay, and then because of the vortex interaction, after that, after x by equal to 1.2, it starts increasing slightly again. And This is at a different angle, but you can look at the pattern, which is very similar. So what I'm showing here is the non-dimensional circulation. So the circulation is increasing from 20% to all the way to around 80%, and which is again because the vortex size is increasing. And after that, as the vortex size starts decreasing slightly, the circulation almost like decreases a little bit, but after that almost remains constant. Now, we saw that two vortices, we characterized them, we found that how they're developing outside the base. Now the important question comes that how do they meander, right? So meander or wander. So basically, if you look at the vortex, they will do like this. The vortex center will do like this at their given position, or it may be random. It may go anywhere, right? And that has got a detrimental effect on the performance as well as the aircraft which is coming behind that. So I'll just show you one video. Okay, so this is the kind of you see the structures, right? So this is called crow instability. So very large instabilities in the vortex that you can see. Okay, although those vortices are developed from the trailing edge of the wings, not from the after body. Okay. There are some experiments also to study this kind of instability. And there are experimental studies to look at the after body vortices also, like our effort. So this is one from the experimental effort by Bleacher and Alcon. These are the computational effort, and this I already talked about that how they are detrimental to the performance. So what I did is basically I look at the two vortex. I found their vortex center and I just plotted them with time. So how their position in y and z. So now I've taken a vortex at a particular location. Okay, so x by L equal to let's say 1.4. So 40% down the body. And then I want to see that how their position at the given location. The location I'm not changing. Location I'm keeping fixed. Okay, the x location, the axial location. And then I'm seeing that these vortices that we have, how they dance with time. And I'm plotting their basically trajectory and the YG plane, right? So you have a, so if I think of like this is my aircraft, right? So I am cutting here, the vortex here, right? So I have a two structure like this here, right? And then this is my YG plane, right? This is my X plane along that. So at the X plane, I cut it. I have got the YG plane, and YG plane, I want to see that how these vortices are changing the position. Both the left vortex is the red one and the right is the blue one. So watch this movie carefully, okay? And then we'll discuss. So these vortices are moving and I'm plotting their vortex center. So you would see that a very random thing is coming up, right? I mean, nothing is making sense as such. It's looking completely random. It's going anywhere, right? So that's what you would expect, and that's what many people initially thought also, that this vortex melting is a random phenomena. But I mean, it's very difficult to model it or characterize it, right?
So I'm sorry, I'm interrupting. These are at what location after the bluff body, sir? At what location?
X pi equal to 1.4. So X pi equal to 1 is the end of the body.
Okay, sir. Thank you.
Up 40% from that. Okay. Yeah, no problem. You can ask questions. Right. So again, these are the same vortex I have shown here. And I try to get the amplitude, the maximum amplitude. So what is AM here? So I have a mean vortex, so which is shown by this purple dot. And I have the location of every single vortex, the instantaneous vortex. So what I do is basically I subtract the position of every single vortex. I square it, divide by the number of vortices we have, and take the square root. So basically, this is the RMS of the amplitude, right? And it, although they both are looking very different in trajectories, their meandering amplitude is almost the same, right? So remember that both the vortices are developing from the same base. Okay, there is no nothing to favor one vortex against the other, and that is what is seen here also. That although they are following different trajectories, the net effect is the net amplitude where they can go, or the RMS amplitude remains the same. We also did the correlation coefficients. So basically, how are the left and the right vertices are correlated, right? So basically, if you know the correlation coefficient R, so basically I take the left vertex and the right vertex position at different time, right? And use this correlation factor, and which comes to around 0.1622, which is not a very big number. But remember that I'm using only the V and W velocity. Okay, so whatever you're saying is basically the velocity on the plane. There is no axial velocity. So the axial velocity is something in the stability language. It is called like a screw. So there is a screw which is working on a strain. So you have a strain field which is due to the V and W, the in-plane velocity fields, and there is an axial velocity which is coming here, which is acting as a screw, and which can make this flow either stable or unstable, right? So that is typical language of the vortex instability. So what I'm showing here, that the vortex are not very correlated to each other if you are only considering the in-plane velocities. If you consider the third component, which is the axial velocity also, there will be something else, and which we'll discuss when we go to the stability analysis. If you take a spectral signature, so put a point probe on one of the vortex or either of the vortex, okay, and just see what is spectral signature. So the spectral signature is very, very low. So it's around 0.3. Okay, so which is a very low frequency compared to the other activities involved. For example, if you measure the shear line stability, that will come around 1.2 or so. Right, so it's very low frequency. And the low frequency is one of the characterization of this meandering phenomena. So I'm talking about the afterworthy vortices, but even if you go for another kind of vortices, for example, if you take what happens, the wingtip vortices, there also you will characterize this vortex meandering by the low frequency phenomena. Okay, now I want to do some analysis. Okay, so because these are the unsteady flows, so we have several tools to study these kind of things. So one we just discussed is the spectral tool to find out what is the frequency involved. So is there any dominant frequency? And we found out that there is a dominant frequency of around 0.3, which is present in the flow. Secondly, you can do flow decomposition. So there are different kind of decomposition tools. You have the POD, you have property orthogonal decomposition, or in biological language, it's also called principal component analysis. There is a DMD, okay, dynamic mode decomposition, which is also have done, but I will not show today. Okay, and then we have EMD, empirical mode decomposition. So different kind of flow, you can decompose the flow, and you can analyze the flow field. And the third tool I will be using is the stability approach, which I'll come shortly. So how does this decomposition tool work? So you have basically data set, right? So you have snapshots. So at the end, what you have, like either you do computation or the experiment, you have basically the instantaneous flow field at different times. So we call that snapshot, right? So each vertical line that you see here is basically the snapshot. So you have I equal to 1 to n is the number of snapshots. So I basically arrange them vertically like this, right? You see the space and time. And then what you do is POD is basically singular value decomposition. Right. So what singular value decomposition does is basically it divides the flow field into two parts. You have space and you have time. So it's basically divided in space separately and time separately. So it's little bit like variable separation approach in the differential equations. Many of you do in your mathematics, right? So basically it's a separation of variables. So I've separated the spatial modes with the temporal ones. So temporal one gives me the dynamics, and the spatial one gives me the structure, right? And then I rank them based on their energy, which is here the singular values. Okay, so it's very close to like U sigma V transpose equal to a given matrix, where U is the left singular vector, V is the right singular vector, and sigma is basically an energy or the singular value, right? So what is the advantage of this approach? That it tells you whether the system is low rank or high rank. What does it mean? So low rank in the sense that suppose you have a flow past a cylinder, right? So if you are doing study flow partial cylinder low Reynolds number, let's say Reynolds number of around 50, right? You would see that there is just one frequency involved, the vortex heading frequency, and you will have like maybe 1 or 2 modes which are different. After that, it's the repetition of the modes. Okay, so but if you go to high frequency, high rank model, for example, turbulent flow, let's take the flow partial cylinder at Reynolds number of 10,000, right? You cannot build the same low rank model in the sense that so these are the rank, right? So first rank, second rank, third rank, fourth rank. So these singular values are the rank. So suppose I can say that I can reconstruct my 90% or 95% of the flow field by just using my 2 modes, right? So then it's a low rank system. And suppose I say that even if I'm using hundreds of modes, still I'm not able to recover my original flow, even up to 90%. Then it's a high rank system. So what I'm trying to study here is that I have an unsteady vortex system, and can my POD help me identify whether the system is low rank or the high rank? Okay, because we saw that it's very random. So whether it's completely random or if there is some kind of correlation or some kind of symmetry is there which is help me characterize the flow. So again, the same thing is written here, that your snapshot, which is here, the QXT can be written as the Q bar, which is the mean flow, and plus this sigma is basically the energy or the singular value, phi is the spatial mode, and psi is basically the temporal modes. Just to give you one example, not the movie not playing. So this is how is the flow partial cylinder at 40 at actually R equal to 100, right? And this is how the periodic energy look like, and this is how your modes look like. So this is the vorticity, the mean vorticity, and this is the instantaneous one, velocity field. So these are the modes. This is how it look like, and if you add different number of modes, you will find the flows which are basically resembling this original flow. So that's called a reconstruction of the flow. Similar thing happens with DMD also, but I will not go into the detail here. Okay. Now, if you look at do the POD analysis on the vortex, so because both the vortices are symmetric, I'm just taking one vortex here, and I'm taking a location at 20%. So it's on the base. Okay. So the 0 is upstream apex, and 20% is just on the base. I'm cutting there, and I'm seeing that how does it look like. So this is my mean flow, and this is my first mode, and this is my second mode. First POD mode and second POD mode, and you can see that there is a nice separation between the blue and the red one, and but it is not very nice in the phi 2, which is because there is a component of the shear layer there, and I will show you. So if you go to x by L equal to 1.0, right? So you have a nice vortex here, completely a nice vortex. And you would see that these are very nice elliptic structures. Okay, there is one ellipse here and 2 here. So, and one here, this is phi 1 and phi 2, the first POD mode and second POD mode. So they are called the elliptic modes. Okay, so these elliptic modes are basically M equal to 1 elliptic mode. So M is determines how many number of lobes you have. Okay, this is again the stability language. So basically what happens, these elliptic modes sit on this vortex, and suppose you overlap this vortex field on this. So what will happen, the blue side will increase on this side, right? And it will decrease on this side. So the core will move in this direction, right? It will become clear in the next one. No, probably the next one. Okay. Let me go there. Yeah. So this is my mean vortex, and these are my modes. Okay, the first POD mode and the second POD mode, and you see that how nicely they look like, right? So they are basically the dipoles, right? And if you present them, so these two mode is like this. They're inclined at the angle of alpha, right? Compared to this angle, they are inclined at angle of alpha, and these are inclined at the angle of alpha 2. So alpha 1 and alpha 2. And if you subtract them, so it will become around 90 degrees. The angle between this line and this line, that's around 90 degrees. Okay. or maybe this line and this line. Okay. So which means that they are orthogonal to each other. The modes are orthogonal to each other, and they basically interact with the mean flow and give you different kind of meandering effects. And how do they give? So in order to understand that, what I do is basically I first put this first mode onto the flow. So I'm just showing you the first two modes, but there are thousands of modes. Okay, so when I did POD, let me just go back to the slide. Here I'm showing you up to 20 modes here, but it has been done by using around 2000 PODs, 2000 snapshots. So 2000 snapshots means 2000 POD modes. Okay, but I'm just showing you first 20 modes. And why I'm doing that is because if you just look at the first two modes, they constitute about 35% of the energy. See, the left vortex and the right vortex both. So by the time you go to the 20 mode, you have already basically capitulated around 95% of the energy. After that, the energy content is very, very low. So that's why I'm showing you just up to 20 modes. So by this time, you might have guessed that this is going to be low rank system, because if the two modes itself, the first two modes, the total energy is 100%. The first two modes itself is giving you 35% of energy. If you take maybe two more modes, so maybe 15% more. So first four modes is giving you 50% of the energy. Okay. Now what I do is that I just overlap this into this, and I see that how the vortex is moving. So as I discussed that if I put this here, the red will increase on the left side and the blue red will decrease on the right side. So the magnitude of this is very high. This you should notice. This is between -10 to 10, and this is -0.5 to 0.5. And why is that? Because this is fluctuation. This is what you call as the turbulent fluctuation. This is the mean field, and this is on the fluctuation. And I'm doing the POD mode of the fluctuations. Okay, I'm taking the mean out. I'm taking the fluctuations of the POD of the fluctuations. So that's why its magnitude is very small. So it looks like comparable, but the scales are very different. It is 10 and it is 0.5. So when you put this one, it will slightly increase on the left bottom like this and decrease on this side. So the core will move in this direction, right? Similar effect will happen in this direction. So what phi1 will do, it will ask the mode to move in this direction like this, along the orientation of the mode. What the phi2 will do, it will ask the vortex core to move in this direction, right? And I will show you that a combined effect of these two modes will make this complicated path that we just saw, the meandering path. Okay, so this is just by adding the first mode. Okay, so I just added the first mode, and I'm again plotting it, and you can see that the core, which is the basically the white one, now has gone to the black one. So it has moved a little bit in the direction of this. Similarly, when I added just the second mode, so it's not very clear on the left one. Sometimes it's not very clear because the movement is so small, right? But you can still note that it is making the core move in the other direction. So what I'm doing here is basically I'm just adding the first mode. This is Q1. I'm just adding the second mode, and I'm adding both the modes, Q1 and 2. And this is my actual meandering path. Okay, this is what we saw in the movie earlier. So let me play this movie again. See, so what first mode is doing, it is actually asking the core to move only in this direction. So I'm basically decomposing the flow completely, taking that what each mode is doing to the flow. So the first mode is just asking it to move in the left-right direction. Q2 is basically the top-bottom direction. And when I'm just adding these two modes, you have a flow which is very close to the actual meandering. So although it may look like that it's a very random field, the meandering is a very random phenomena, it is not. It is basically happening because of this two modes which are present here, and their different energies. And when they combine together, you make this complicated flow field. This is in the left vortex. This again, if you measure the angle of this is alpha 1 and alpha 2. Okay, so the combination of both modes gives a complex trajectory, and it's very nice if you some of you are interested in drawing. So there is a Lizard's curve, which actually takes a different kind of linear paths and gives you very complicated structure, and that is what is happening here. Okay. Similarly, if you look at the right vortex, okay, so same thing is happening, first mode, second mode. So one is asking on the left, right, second is going on this direction, and the combined effect is Q12 here, and this is your actual configuration. So although see, there are some differences, okay, and which is expected because I'm just using first two modes, right? If I'm using 10 modes, it will be much more closer to this, right? But still, with the just two modes, you're able to reconstruct or at least get the direction of the movement, right? So that's a good big thing. At least it tells you that this meandering phenomenon is not a random phenomenon. It is happening because of the certain elliptic instability mechanism right at the heart of the vortex. Okay. Yeah, so with that, I will take a break and I will request you to ask questions if you have any, and I'll move again. Okay, and I'll cover the last aspect, which is the stability dynamics. If you have any question.
Yes, sir, I
If
have a
not,
small doubt. So
yes.
how do, like, boundary conditions are taken care, like, in LES? Just like, normal, can we specify just the mean velocity, or how to specify boundary conditions, let us say, at the inlet, maybe?
No, inlet, I told you, we have a boundary layer profile, right? So the boundary layer we got from the experiments, and we just imposed it there. So the inlet is somewhere away from the upper body, from the base, right, ahead of the base. We just put a basically the boundary layer that we get from the experiment. It actually can do the flat plate boundary layer also, and put it there, right?
Okay.
And then you have the wall condition on the base, and away from that, you can have a symmetry condition or anything. So if your domain is very far from the body, you can have an ion bonding conditions there.
Okay, sir. And then I heard you saying that, initial transients, they die down after some time, and then only you are taking results.
Yes.
Something
Yes.
like that. Can you please explain that,
Yeah, so that is true with any turbulent flow simulation. Okay, so you will have the effect of the initial condition in the beginning. So an initial condition is not perfect, right? So initial condition, for example, you can start with any random initial condition. For example, you have a lead-driven cavity where the flow is zero, the velocity is zero. You can start with flow velocity equal to 1. Still, will get the same solution, right? So you will have the initial transient effect. So if you, for example, put a probe somewhere in the flow, right, you will have very random fluctuations going up and down, and it will eventually settle down. Okay, settle down in the sense that you will still have the fluctuation, but it will have a given frequency, right? It will not be very random. So initially we'll have very random thing because of the initial condition. So that has to go down. Then only you should start collecting the snapshot. If you mix that with the if you start collecting snapshots very early, what will happen that you are taking the snapshots which are transient, which are not basically the structure of the flow. That is because the flow is still developing.
Okay, sir. And sir, can you please tell us some reference on proper orthogonal decomposition for turbulent flow? If you can tell us some book or some.
Yeah, so yeah, I can give you. I mean, we can maybe I'll send it to email to Dr. Kishore, and he can send it to you. Okay, POD. It's a very beautiful tool, and I will recommend all of you. And it's not very hard also implement. So because a lot of you work on the unsteady flows, so it's good to have these kind of tools.
Okay. Thank you, sir.
Yeah. So I already have like 15. So I'll go through the one last aspect, which is again application of a tool which is linear stability analysis. So people normally perform this in stability analysis on a very simple canonical flows, for example, on a flat plate or a basically lead-driven cavity or open cavity kind of thing, because these are very, very expensive. And just to go back to the history a little bit on this. So this approach has been developed to study how the flow becomes transitional from a purely laminar flow or stable flow. So if you have any stable flow, if you increase Reynolds number, first what will happen, you will have some fluctuation. So you will, first the symmetry will break, then it will become periodic, then it will have like more frequencies. So like multi-periodic kind of system, then it will become aperiodic, means it is no longer periodic, there are several frequencies present, right? And then it becomes transitional and then turbulent. So the linear stability tool was used to understand if there is any mode which is present in the flow, which can make the flow unstable and hence transitional, right? So you would often hear the number term called the critical Reynolds number. So the flow below the critical Reynolds number is basically stable, and above the critical Reynolds number is unstable, right? So we'll be using the same concept here, but here the flow is no longer laminar. So here the flow is a mean turbulent flow. So there are recently, these are some development that if you have a turbulent flow and you can get a very nice mean, long-term mean, you can use the same kind of dynamics to see whether this large scale dynamics show any kind of instability. So that is what I'm going to discuss today. So this I discussed earlier also, there are different kind of instability that you can study. One is basically the meandering of the vortex that we just discussed, which is this kind of convective instability, local instability. And second is the global mode. So basically you can have instabilities on the base also, the three-dimensional stability. So we'll not be discussing on the three-dimensional stability today. We'll only be discussing on the stability on this vortex meandering. Okay. So we'll go to our ideal system, because as I told you, these are classical tools. The linear stability analysis is a classical tool. So you cannot use in the random flow. You have to basically characterize to a given flow field, and then you can use it. So that's what we will do, that we'll consider a vortex system. And there are two things we have. One is the axial flow, how the axial flow is changing. And then we'll map to a given vortex. So what we are doing here is basically, the top one is what we got from the simulation, okay, from the large AD simulation. And bottom one is basically, we are mapping it to a mathematical vortex, which is bachelor vortex. I will just show you in the next slide. So we have the u velocity, the axial velocity, and the inclined velocity v and w. So you can see that there is a very close resemblance between all of this. So the issue with doing with the flow vortex, which is the actual flow that is coming from the LES, is basically it is too complicated. You have effects due to the shear layer. Flow is mired with different kind of small structures. So what we are interested in basically is the instability in the vortex itself. Okay, that is what, or the vortex pair itself, not because of the other surrounding phenomena. So that's why we model it to a mathematical vortex, and the mathematical vortex is given by this bachelor vortex. Okay, so basically now we are moving from the three-dimensional system to the polar system. So x, r, and theta. So you have an axial velocity, which gives you the kind of screen effect that we call, okay, all the strain, and the theta is basically the swirl, the vorticity field. And basically this is how we have characterized the vortex. I'm not going to the detail here. And how do you perform the stability analysis? So you have equation. You can write the Navier-Stokes equation in a very compact form like this. Partial q by partial t equal to fq, right? So the f is basically all the convective term and the viscous term and everything on the right side, right? The pressure term, pressure gradient term, so everything on the right side. And then you put a small perturbation. So the way stability analysis works is basically you have a flow and put a perturbation on top of that and see whether the perturbation is growing or decaying. If the perturbation is growing, then the flow is unstable. If the perturbation is decaying after some time, then it is unstable, right? So then you put this perturbation, and then when you put the perturbation into this Navier-Stokes equation, you have a equation called linearized Navier-Stokes equation, right? Basically, you subtract the q bar will also basically support this Navier-Stokes equation. You subtract this from here, and you have an equation in terms of the perturbation. The q prime is the perturbation here. Okay, and then you assume a form of the perturbation, which is basically a Fourier form, q hat x e to the power I omega t. So if it's spatial, then it will be kx minus I omega t kind of thing. And then you basically formulate an eigenvalue problem here, aq equal to I omega t. And you solve this eigenvalue problem. That the eigenvalue of that will tell you whether the modes are growing or decaying. Okay, so I don't have time to go into the detail here. Just go through the results. So this is how my grid will look like. So if you have a vortex, one vortex here, put a vortex there, make a grid like this. Okay, very fine, close to the vortex, and coarse away from the vortex. And then you have different ways of doing this analysis. So I have developed a code which is called PeakStab. So it can do different kind of analysis. So temporal analysis, spatial analysis, different kind of grids you can use. The flow can be incompressible or compressible. So there are different ways you can do that. Okay, so these are some of the validation. So the one which crosses the zero axis, right, that becomes an unstable mode. So everything below zero is basically stable. How is that? Why is that? Because e to the power omega t, right? So if omega here it becomes omega I. Since omega I is positive, then e to the power omega t will always grow, right? If the time is growing, it will keep on growing, right? If it is omega is negative, so all these values are negative, right? So then the flow will be always stable, right? Because e to the power minus omega t is going to be stable with time. Similarly, you have in the k, it is just opposite. This is a spatial one, where instead of frequency of the wave number, right? So if the value is negative, in this case, it is minus kx. Okay, so then if it is negative, then it is growing, right? So it is marked here. So these are some of the validation that you can see that our code gets the similar values as in the literature. This is a typical mode shape for a single vortex. Now there are some tricks here. So all is good for the one vortex. If you have two vortex, you have to be more careful because you have to resolve the space in between them. So that's what we do here, that we resolve the spacing between the two. In this case, this is a Chebyshev grid, and we use a kind of mapping here. This is called the tan H mapping. Just to show you the result, that if you have just one vortex, okay, there is no instability. You can see everything is below zero, right? No mode is crossing zero axis. And I have shown you the grid sensitivity studies also. At 60 cross 60 and 70 cross 70, all the leading modes are converged. Okay, this difference that you see, that is expected to be there because we only converge the leading modes. And the mode shape that you see here, this is again the fluctuation, is very close to the POD modes that we saw, right? The dipole that we saw there. But if you take the two vortex, right, the vortex pair, you will have an instability, as you can see here, that one mode which is coming and crossing the zero axis. What is happening is that two vortex and the axial flow in between the vortex, right? So that act together and give you an stable mode, whose shape is very close to the POD mode that we saw. And this mode is responsible for the meandering of the vortex. Okay, so we argued it from the physical point of view also, that there's an inherent instability because of the vortex-vortex interaction, and that leads to the meandering. Okay, so with that, I have a lot of things to say, but I don't have time, and maybe at some other time I'll just go to the conclusions, and then I'll take some questions, because that will be more interesting.
Hello, participants. Please share some doubts if you have with the Professor Ranjan. We can take some quick questions. We have time. So please raise your hand and share your questions. Ask the questions.
Yeah.
Hello. Anyone from the participants? Dr. Ranjan, actually, last time I was asking some questions, then some network hiccup happened here, and I couldn't
Okay.
actually complete. I would like to
Sure.
go ahead with that.
Sure.
Like you said, this is kind of a horseshoe vortex, as you said, some plane surface, and some
It looks like a
meandering and
horseshoe
all.
vortex.
Yeah. And there will be some other vortex, so many coming out from the blade and all. So I think your simulation is just focusing on that from the wedge end, right? Not like the vertexes coming from the outside horseshoe, which is the big horseshoe, as you called, and the small, which is generating because of the uplift of the airplane and all.
Yeah.
I was a
So
bit curious because one image you, the video you showed where this vortex was very much stable, and so that's what I wondered.
no. So see, there will be only two main vortex. Okay, the longitudinal vortex that you have, that you're seeing here in the picture. Okay, but around that you will have a lot of activities. But eventually, you will not have a lot of vortexes forming. You will have one vortex which will be sustained in the flow. Okay. So it's unlike in the flat plate, we'll have a lot of vortices which are arranged either in the symmetric or the anti-symmetric manner, and they give the lift-off effect. So it looks like a horseshoe vortex, but it does not have the same character as the horseshoe vortex that we discussed in the context of flat plates.
Okay.
It's only the shape is very big, and the length is very big, and it looks like a horseshoe vortex.
One more thing I would like to ask, because you're familiar with both LES and DNS, and these are like mostly the boundary layer thing where the vertices are very small near the boundary and all. So how different it could be in terms of physics wise and in terms of computational power, I would like to ask. When you go ahead with this LES and the DNS which you have for the curvilinear coordinate, computational cost wise, are there any advantage to go ahead with the LES or DNS and LES? Like what could be the
So
if you do some optimization in grid and locally refine the grid in the complex region, computational wise, like how much difference these two could make in high fidelity simulation?
See, so first of all, I want to tell that in this particular simulation, we are not using any explicit model. So there is no Smith-Garamsky model which you typically use in the LES. Okay. So for all practical purpose, it is a low resolution DNS. Okay. So what is DNS? You don't use any model, right? So the same thing is happening here also. That we are not using any explicit model for the smaller eddies, right? So it is for all practical purpose, it is DNS. So if you increase the resolution, if I can answer your question, so what will happen that the number of structures, so we have a fine structure, for example, of this scale, right? So what will happen is you will have even more finer structure, right? So the granularity of the solution will increase, but the overall qualitative behavior that you have, we have a very two large vertices, and then you have activities around that will remain. It will become more and more granular in the sense that you will have a lot of small things which is very close to the vertex. Okay. And of course, computationally, as you know, that it will become much more expensive. If you are, for example, I'm using 60 million grid points. Suppose I go to like 200 or 300 million. So it increases exponentially. The cost increases exponentially.
Okay. So, like as you mentioned in your POD analysis, this is a low rank system. So only starting few more modes actually matters, and that's why probably the resolving to much finer will not ultimately change its overall physics.
Yeah, you can say like that. Yeah.
So I have a question, Kishore ji, can I ask?
Please go ahead.
Sir, actually my question is then how do you decide that, how fine grid should be? Is that depends upon like the Reynolds number, or like what are the guidelines for, that this much grid will be sufficient for our LES?
No, so there are, there are different answers to that question, but the most important is what is the thing that you're looking for. Okay, suppose you tell me that I'm only interested in the pressure field. Okay, so how the pressure is there on the body, on the base. I would say that 60 million is also too high. You don't need that. You don't need to resolve the vortex, right? You can go to maybe 10 million and you can still get the very decent idea of the pressure field, right? So it depends on what kind of questions you want to ask. So our purpose was to look into the meandering of the vortex. So that's why the small structures become very, very important, right? So that's why we had to go to a resolution where at least we could resolve those structures. So I was showing you one picture here. This one. Yeah, this answers your question also, Kishore, Dr. Kishore. So basically, you can see the granularity here. This is actually 200 million. This is again LES, but this is 200 million. This is not our simulation, some other group simulation, right? So this becomes even more granular here, right? Small structures are very, very fine structures are there, very nice structures are there. So again, to answer that question, it depends on what are the fluid phenomena that you are interested in, and based on that, you should choose the resolution. There are 2-3 things that you should keep in mind. One is that there are some abrupt changes in the flow due to the Reynolds number, so that should not happen. For example, suppose you have a turbulent flow, which is happening at say 10,000, and you do the simulation at 1,000 where the flow is still laminar. Then you will have completely different flow physics. So you are not even qualitatively right. But suppose you have flow became fully turbulent at 10,000, right? And then there is something happening at your flight run or somebody, for example, 100,000. So still with the 10,000, you can have a qualitative effect because the flow is already turbulent and there is no drastic effect that is happening there. The only effect that you will have is quantitative, in the sense that maybe the boundary layer will become thinner, right? So when you run off somebody, the boundary layer become thinner, right? But there is nothing happening which is qualitatively changing the physics of the flow. So those are the few things that you should keep in mind, that you should not ignore a particular phenomena. For example, if there is a separation involved, we should resolve the separation. If there is a transition involved, we should not ignore the transition phenomena. So those are the things that you should always keep in mind while doing selecting the graded resolution.
So one more question, sir. Can we do, let us say, LES with second order accurate scheme, or let us say if we have sufficient computational power with first order accurate scheme? Is it possible?
First order is too bad. Okay, first order is too dissipative. Okay, so first order is something I will never recommend. Even the RANs people don't do first order. So what will happen? I mean, think about the first order. The sock, if you have a sock like this, it will be like completely smeared out and it will look like a big, completely going like this, right? So the first order is very, very dissipative scheme. I would not recommend you even for your RANs simulations. People have done second order schemes also with the LES. In fact, I have also done DNS. So sometimes it becomes, it is our requirement, right? For example, if you're going with unstructured grid, you cannot go beyond second order, right? Because you do not have information about the neighbor cells, right? So that is our limit. So what you will do then in that case, that because you cannot increase the order of the accuracy, you will increase the resolution, basically increase the number of grid points, right? So you can do DNS that way also, even LES that way also, but do not go for the first order. Okay, second order and beyond is something I would recommend. Again, there even in the DNS or LES, if you're doing with the second order, use high order reconstruction, right? So the reconstruction of the basically the cell center to the cell edge, right? So they are, instead of using only the first or second order, you can use the third order interpolation or the fourth order interpolation kind of scheme, so that your reconstruction is better. So those kind of things you can do to increase the accuracy of your schemes. So more accurate your scheme is, lesser your grid resolution requirement will be.
Yeah, thank you, sir. Thank you very much. It was really informative talk. Maybe I'll contact you, separately if we have some other doubt. Thank you, sir.
Sure.
Okay. So participants, any other questions? Please raise your hand and can share the doubt with us. If not, then let's thank our speaker, Professor Rajesh Ranjan. Aerospace Engineering Department, IIT Kanpur, sorry. So Rajesh, it was really a very insightful talk, and you have covered this the very various field like the LES and the POD, and how you have shown that the POD can actually help us in judging somewhere. In fact, the requirement of grid, saying that how refined and how complex the physics is, and what how the stability should be. So thank you very much, Rajesh, for this talk.
Yeah. So yeah, I mean, it was a great honor, and I hope you have something to take away from there. That if you have an unsteady flow,
Right.
do not get basically threatened or something. You have a lot of tools nowadays to analyze these kind of complex flows. So
Okay, one thing I would like to ask, let's say someone is using the proper decomposition POD mode before going ahead with their actual analysis to judge that how complex my flow physics is and how something. So they need some kind of the data, right? Probably if suppose the experimental or something like if they have. So minimum how many frame someone need to have to just do some kind of pre-analysis regarding the complexities of a flow? Like how many frame is mostly needed to?
It depends on the frequency of the flow. Okay, what frequencies you have. So suppose if your frequency is very high, the number of snapshots will be very large. Right, it's typical Fourier requirement. Right, if you are doing the spectral analysis, if you want, so the frequency is inverse to the time, right? So if you have very high frequencies, then the temperature will be, so the time will be basically small, right? So if it is low, then you have to take a very long time step, right? So the same requirement is here also. So if you are really interested in, for example, the separation physics is very low frequency physics, very, very low frequency. So if you want to find out that how the separation is happening somewhere, you have to basically really integrate for a very, very long time, right? So whatever the spectral physics is telling you is applicable to POD or DMD also. So it depends on the inherent physics of the flow. What is the frequencies involved on those things?
Right. So once again, thank you, Rajesh. Actually, at that moment, some doubt came to my mind, saying that what this could be a pre-tool to judge the complexity of a flow.
Yeah. Okay.
Okay. Thank you very much. So participants, our next talk will conduct here itself in this session, inaugural session only. The title is still showing the inaugural session, but actually we are covering the whole today's talk in this session. And our next talk will be by Professor Iru Banoth, and he will be talking about the microfluidic system. And the next talk is going to start at 4:15. 4:15. So I request all of my participants to join us at 4 o'clock. And in the meantime, we thank Rajesh for this wonderful talk. So participants, let's join for the news third talk of this session, 4 o'clock.